Thank you for joining me at this year's virtual PEGS. And we've been at PEGS many, many years. But this is the first virtual version I ever do. We're looking forward to this. My name is Klaus Gustafsson, and I am one of the co-founders here at Atom. I will talk to you about our integrated antibody development pipeline that we built over the last few years, and I will include a couple of case studies that I think you'll find interesting. First, a few words about the company. Some of us may not know about Atom, but you may know about DNA 2.0. That was the old name of the company. We changed name back in 2003 for various reasons. And this, at the same time, we also acquired an antibody company called PEGS that was developing high throughput antibody production processes. We're based in the beautiful San Francisco Bay Area. At this point, around 105, 110 employees, and been really focusing around building the technology and to industrialize biotechnology. I'll talk a little bit about what we do and how we do that. The other thing we're really excited about at this very moment is, in addition to our existing facility that we moved into back in 2016, that was at the time built to a state-of-the-art laboratory to really support our production platform. We now are in the process of moving into building number 2. So we acquired this building some time ago, and now we're under construction, and we expect to move in December of this year. And this will allow us then to further increase our production capacity and our support for antibody development. As we all gone through the last probably 6-7 months now of COVID and all that comes with COVID. I think when COVID first hit back in February, we weren't really sure what's going to happen to the company, because as a fee-for-service company, we're really dependent on customers coming to us for support, and many companies just shut down and did shelter in place and didn't do any work. At the same time, what we also saw is there quite a few in the biotech space, in the pharma space, shifted towards a very aggressive focus around building diagnostics, building vaccines, and certainly antibodies, neutralizing antibodies against COVID. And so turned out, I think March and April, the last few months, been probably are the most hectic months ever in the history of the company. So it's really been interesting to see how the tools that we've been building internally to industrialize biotechnology has really been applied now with the urgency that is required to stamp out this ongoing pandemic. So back to the company and what we've been building. So really been focusing on setting up a nice infrastructure, allowing us to build synthetic genes. So we're building an order of millions of synthetic genes. And once we have the genes, we can of course make those into proteins. So tens of thousands of proteins, and then of course hundreds of cell lines over the last few years as we've been scaling up this process. And this process is really built on an underlying infrastructure that is highly dependent on the LIMS and a very ambitious sample tracking, barcoding, and infrastructure around logistically mapping all these elements in this underlying process. Even though we're a small company, we're 100 or so people, I think we have probably 10% of our employees are software programmers, database people, allowing us to really enforce a rigid structure and maximizing the information content. We always joke that we thought we were a biotech company, but turns out we're really a logistics company, as all these bits and pieces in the process continuously talk to our underlying LIMS to make that happen. So not only do we have a very large, ambitious software core that supports our manufacturing platform, we also built a number of unique tools. And so I kind of placed a lot of these technologies And the way we see biotechnology, so we see it as two axes basically. One is the manufacturing axis. How do you make genes? How do you make proteins? How do you make cell lines? What is the infrastructure? What is the instrumentation, the chemistry, the molecular biology that goes into making these as efficiently as possible? On the y-axis is really a question of building up the machine learning tools. Well, how do you design better genes? How do you design better proteins? And how do you design better cell lines? So it took a lot of these tools that we developed, and all the ones in yellow are the ones we have IP protection around, and kind of parse them out across the spectrum, not to illustrate any particular technology, but really to state how all these tools and technologies together form a platform that we can then apply to production of these biological entities. So here's a nice case study we did fairly recently in the era of COVID. So one of our customers came to us and with very urgent requirements for making antibodies, neutralizing antibodies. So the sequences were derived from recovered COVID-19 patients. And so by doing deep sequencing, this customer identified a number of different sequences that were likely to be interesting candidates for neutralizing antibodies. We took those virtual sequences, we designed them using our proprietary algorithm for codons on mRNA structures and all that, and synthesized the corresponding gene, cloned them using our proprietary electrocloning, transfected them into mammalian cell lines, and expressed them in 100 mil scale, and then purified them. So from start to finish, from 70 antibodies that we're doing, it took us, the first one came through the pipeline in 18 days, and the very last one of the 70 took us 24 days to completion. So in 3 weeks, we processed 70 antibodies at what we call COVID speed, and with an average of around 50 mgs. So these were, as you see here, the average titer, of course, ranged from the poor worst ones around 200 up to 800 plus mgs per liter, but with a mean of around 500 mgs per liter. So very productive, very efficient scaling, and rapid high quality antibodies were generated in just 3 weeks, which is probably twice as fast as anyone else in the industry. I'll also talk a little bit about how we utilize our platform to engineer antibodies for developability. So here's a case study where we took an antibody that's already on the market, has been on the market for a long time. We identified 41 residues in the heavy chain and 36 residues in the light chain that we thought were interesting to modify. So the full combinatorial of that space is in the order of 10 to the 23. So, which of course is a massively large space and something you could never ever in 1,000 years screen by phase display or something like that. Not only did we want to optimize it for affinity maturation, but we also needed to increase the melting temperature for stability, increasing stability of this molecule, and also want to retain or maximize the yield. So we optimized for 3 different dimensions. And we identified amino acid substitutions to swap out using our in-house database and variable selection theme around, which is focused around the existing sequences that you can find in various germlines and public databases, and comparing those with sequences that had never been made, and identify things that, according to the rules of Mother Nature, allows us to fold proteins properly and manage good sequence integrity, and allows us to be much more likely to be successful proteins. Taking these substitutions, we are now made a set of 96 of only a very small subset. So 96 antibodies were made. As you see here, this is what we call a matrix plot. So on the x-axis, you have 96 antibodies in the blue round. So antibody number 1, for instance, has no substitutions at all in the light chain, and it has 1, 2, and 3 substitutions in the heavy chain. And of course, this substitution here is also seen in antibody number 4 and antibody number 10 and 11 and so on and so forth across. So all these substitutions are systematically varied using a design experiment. So synthesizing, designing these in silico, and then physically making them, and then testing them for binding. We combine them and identify the good binders, use machine learning to identify the substitutions that make them into good binders, identify the substitutions that make them the others into poor binders, get rid of those. And as you see going onwards here in the pink round, what you see now is that we freeze some of these really good substitutions in, so they now become constant throughout this entire data set. We get rid of all the substitutions that are poor, and basically just big void. And everything in between where we don't have enough information, we again systematically vary them according to the standard experiment algorithms. So the point I want to make here is that even though the space is 10 to the 23, which is of course an enormous space, because we use systematic variance, we identify in this, I think 77-dimensional hyperspace, we identify 96 orthogonal corners that are equidistant from each other, and then basically become the most information-rich nodes in this space. Making them, testing them, we can then identify how the valleys and the mountains in this space, and identify how to walk towards the mountains. So as we go through this round 1 to blue round to pink round, we get rid of a lot of substitutions and really rapidly funnel down the substitutions into much smaller space, that is 10 to the 4 here. And then subsequent cherry picking off of the 10 to 24 space, we get another 5. So the point I want to make here is that you see in the blue round, we're looking at binding now on the y-axis, as measured here as Ka. Most of the sequences are worse than the starting point being the red. Most are worse. A couple of guys are a little bit better, but the nice thing, you see this even nice distribution across. So that makes it easy to model, capture good information. And then you see in the pink round, basically every single clone in the pink round is better than the starting point. So not only do we get a couple of hits, but we really move the entire population and sequence function space into an area that is much more prone to have good activity. And then identify further subset that are really interesting. Now we can take those sequences and we can plot them here, in this case, not only for binding, which is on the x-axis here, but also for titer on the y-axis, and in this case, Tn as coloring scheme. So we took those 180 some sequences, a very small subset of sequences, and tested them. So here you have the parent up here, and as you move towards better affinity and then an increase in titer and Tm, now you can identify a number of sequences that we can look more carefully at and pull those in this case 3 of those guys out here, and you see you rapidly can navigate in multidimensional fitness space in a consistent manner. So the last few minutes of this talk, I'm going to focus around our transposon technology, our cell line development technology, which is based around using transposase to rapidly move genetic elements into the chromosome of mammalian cell lines. Of course, transposons have been around for a long time, discovered by people a lot smarter than us. So Barbara McClintock really deserves the honor of this. She did also get the Nobel Prize in 1983 for transposons. The family of transposons we've identified and then further engineered using our protein engineering platform allows us to very rapidly build these cell lines. So I'll talk a little bit about the process and how we do that. We call them leap in, and it's just a family on the transposase tree. What we end up doing when we use these for building cell lines is making plasmids that are the genetic element of interest, typically an antibody, is flanked by ITRs, inverted terminal repeats. And they are then flanked by these TTA sites, that is the location sites in the plasmid. We then can co-transfect that vector together with a transposase, the enzyme, and here we supply that as mRNA. So we co-transfect the plasmid DNA with the antibody, with the mRNA contains the transposase into the cell line. and we get these multiple single copy integrants across the genome of the cell line. So this is really nice because every single insert that comes in, so it's a nice little slot in, it's a nice little cassette, independent from all the other locations. And you get multiple of those integrations across the genome. So when you do classic homologous recombination or non-homologous recombination based integration, you typically get a lot of these concatenamers, you get a lot of inversions, you get truncations, you get all sorts of genetic instabilities happening due to the recombinational frequency of the insertion, which is basically you're selecting for that because that's what your selection marker strives for. And that's the reason why you get all this instability and all these very weird formations. Whereas when you do it, we're using transposons, now you get this nice consistent cassettes where everything is exactly as you design it, slot in, cassette over cassette over cassette across the genome. It gives for a much more uniform distribution. So why is this nice? Well, one thing is that you get multiple copies that are really behaving as independent entities. So in your pool, you will see that the absolute majority of your pool is going to be very high expressing clones. So you get only a very small subset of your pool is going to be poorly expressing, but basically everything in your pool is going to be a nice, a good clone. And that distribution then allow you then to we typically only screen for, say, a plate or so worth of single clones to identify our winner clones. And often we just go straight from the pool, depending on what you want to accomplish. And here's just a couple of examples of antibodies and represented a pool titer. And the nice thing with a pool titer will mimic very closely what we see as the final clonal titer. Another really nice feature of this is that they are incredibly stable. I mean, transposons they have evolved for 4 billion years with a one selective trait being stability. So what we see in the case here, we're looking at nine different clones from day 0 to 60 generations plus minus selection pressure. And we see basically completely stable, both on productivity level and also on copy number, all across the 9 generations. And we have multiple studies of this showing this incredible stability that we see accomplished using transposons. And another nice thing with building these tools is that allows us then to put very large pieces of DNA into the vectors. So we can basically have more or less infinite amounts of DNA into each vector as being transposed using the transposase into the genome. So now you can build 2 or 3 or 4 cassettes that go in. And as you get there, you can start building different promoters and different elements. So here's an example where we look at different promoters to look at the ratio between the pink ORF and the blue ORF. And as you see, we can across these 14 different clones, we have 14 different constructs. We can very narrowly navigate the ratio of the different clones. As we build this tool now, we can set this up to very efficiently move from virtual sequence to physical gene sequence to a stable pool to start doing the cell line cloning. And we do all the cloning we do with a Solentin VIPS machine. This is a very good characterization of the clonality of the sequences and move that into RCB. So we can basically go from transfection to RCB in just 12 weeks, really efficient system to allow us to navigate that space. So thank you very much for your time. I just want to reiterate that building this toolbox and this capacity allows us to build genes, build proteins, and build cell lines with unprecedented scalability, speed, efficiency, and quality. So please reach out to me at this email if you have any questions, or pop it into the chat box after this talk. So thank you very much for your time. Appreciate it.